start.
Hi, my name is Rémi Cresson. I am with INRAE at Tetis Lab, and today I will present you a few applications for remote sensing time series preprocessing that use deep learning. In the first part, I will present you the context. Then, we'll see how convolutional neural networks can remove clouds that impact optical images in time series, using time series of synthetic aperture radar and optical images. And then, in the second part, we'll discuss about super resolution on Sentinel-2 images. On one hand, there is more and more data for Earth observation. In remote sensing, there is more and more sensors and more constellation of satellites, which deliver some images which are each generation sharper and sharper. So it is a lot of continuous data stream that reaches every day that we have to process, and it's a kind of computational challenge. And on the other hand, in data processing, there is a major breakthrough thanks to deep learning in many scientific domains, because it's a technique that allows to go large scale and with very good results. For instance, in Earth observation, we can say that land cover mapping has reached a new quality. Same thing in object detection. And today we'll talk about images pre-processing, because that's also a domain which is booming. So the first part is about the cloud removal in optical images. So what is the most cumbersome issue with optical images? The cloud, which pollutes the image. So we did an ongoing project with the French Spatial Agency to assess the deep learning approaches for Sentinel-2 images reconstruction. So the goal is to reconstruct Sentinel-2 images that are impacted by clouds. So we apply and we benchmark state-of-the-art method on realistic data volumes. For instance, we use 10 tiles on the Occitanie area from the 4 last years of acquisitions. And we compare these methods with traditional methods, for instance, the gap filling. And we have a few deep learning based approaches that we try, and I will present you that in the next slides. So first, I will recall what is the gap filling. It's polynomial interpolation in the time domain, and it's daily used to deliver Sentinel-2 level 3 product at the French Space Agency. It uses cloud mask to interpolate the missing parts of the image. And since the cloud masks are not always perfect, it can lead to artifacts in output images, like you can see in this illustration. The first deep learning method that we will test is the single-date convolutional neural network. It's a network that inputs one polluted Sentinel-2 images and one synthetic aperture radar image, and its goal is to reconstruct the optical image. The second kind of methods that we will use is multi-temporal convolutional neural networks. Those are networks that input multiple optical images and multiple synthetic aperture radar to estimate the central acquisition of the optical image. We have 2 study sites, one in France that's composed of 10 Sentinel-2 tiles, and one in Africa which is composed of 6 Sentinel-2 tiles. As you can see, that's a lot of images, like nearly 7,000 Sentinel-1 images and 5,000 Sentinel-2 images. So the first thing is to prepare our data for the training and the validation and test steps. So what we did here is that we have indexed the patches with R trees to be able to query patches that have a certain cloud percentage, that are acquired at some date and that are consistent with some acquisition layout, that is the gap between the Sentinel-1 image and the Sentinel-2 image. This way we can build some datasets for each of the proposed experiments. So for instance, here you see the first network, which use 2 synthetic aperture radar images and 1 synthetic aperture radar image for the central date, 1 digital elevation model, and which estimates a clean Sentinel-2 optical image. So here we need 1 clean Sentinel-2 image, which is here, 1 clean Sentinel-2 image acquired just before, which is here, and 1 clean Sentinel-2 image acquired just after, so that's here. And we have some constraints on the date between the Sentinel-1 and the Sentinel-2 image for each acquisitions. And we use this principle to build some data sets. For each network we have a particular configuration and we can generate a new dataset. Then to train our networks, we use the minimization of the L1 distance, which is also called the Manhattan distance. So here you can say what's the Manhattan distance in blue or red or yellow, which is the same thing. You have the Manhattan distance, what we want to minimize across one batch of patches. And in green you can see the Euclidean distance that we will use to validate our results. We use the L2 norm to compute the mean squared error, which enables us to derive the peak signal to noise ratio. We also compute the spectral angle between the estimated image and the true image. And we compute also the structural similarity index. So we benchmark each network and we compare with gap filling when it's possible, because you cannot compare let's say gap filling with this network. It doesn't work because gap filling needs something like this. It needs 1 clean image before, 1 clean image after, and eventually 1 damaged image in the central date. So we can only benchmark and compare with gap filling on some acquisitions layout. So here are our results. I just recall that we have 2 operational scenarios, namely OS1 and OS2. In OS1, we perform the same thing as gap filling does, meaning we have a damaged image here and we don't want to use it. Instead, we just want to reconstruct it from clean images acquired just before and just after. And we use the synthetic aperture radar image, which is acquired at the date of the image that we want to reconstruct. And in the second operational scenario, we just use every images that we get at input, even if they are damaged, and we reconstruct the image at the central date. So once we have trained our network, we compute all metrics on the validation dataset. Here you can see the results of the first operational scenario, and we compare with the gap filling. As you can see, the results are better for the deep learning based approach, except for the structural similarity on the Occitanie dataset, which is slightly higher for the gap filling. And we wanted to explain why we have a so low PSNR with the gap filling compared to the deep learning based approach. So we look at the generated patches computed on the validation dataset. Here we can see the patches that are computed on the validation dataset from the gap filling on the first row and from the deep learning based approach on the second row. The first column is the optical image, which is acquired just before the image to reconstruct. The second column is the reference image. It's the image that we don't use in the model, but which we use for compute the metrics. The third column is the image which is acquired just after the central image. And finally, the last column is the reconstructed image. So this is the reconstructed image from the gap filling, and this is the reconstructed image from our deep neural network. As you can see, there is one snow coverage here, but after and before there is no snow. So maybe the snow melt between the two acquisitions here. Anyway, the gap filling will interpolate between these two images, and the deep learning approach will use the synthetic aperture radar that we don't see here to derive a more precise estimation. This is another area. We have the same problem over the validation patches, and since the radiometry of the snow area are very high, we think that mean squared error is also high, so the peak signal to noise ratio is really low for the gap filling. So this shows that the use of the synthetic aperture radar image is useful because it helps the network to estimate a more correct output image. So this is the result for the second operational scenario. So in this scenario, I recall that we used every images at input, even if they are full of clouds. So here we can see that we use only this acquisition layout, which is an acquisition layout which is composed of one clean image at the date t-1 and a clean image for t+1. So we can compare gap filling and our trained network on a fair basis. We don't inject cloudy image in the gap filling. So here you can see that we beat gap filling on both study sites for PSNR, but the spectral angle and the structural similarity is better for the gap filling. Even it's quite small, it's a bit better. So here we think that the networks tends to blur a bit the reconstructed images, even if they have a signal which is more close to the actual signal. But the gap filling will tend to generate some images that looks more like real images because it will use directly pixels of the images. Here are a few patches processed from the validation dataset for the second operational scenario. So here we have the t-1 image, the t image, the t+1 image. All three images are impacted by cloud. And the two last columns are the estimated image on the left and the target image on the right. So the target image is the actual image that we just used to compute the validation matrix. So you can see that our input images are very cloudy, but we reconstruct something which is a bit blurry, but more looking like the reference than the input images. So we can see that the network is able to use the available content of the input images to reconstruct the output image. So when there is too much clouds, you can see that some areas tend to be a bit blurry. It sometimes fails to reproduce correctly the some textures, for instance the tree canopy here. And the last experiment that we performed is the convolutional neural network that inputs one single optical image and one single synthetic aperture radar image. We cannot compare it with the gap filling, but we have compared it with the multi-date convolutional neural networks that we used just before. And we have compared it on some acquisition layout that allows it, namely one acquisition layout that has the same properties for the central image, the S2 at date T. So we can see it's not a surprise that the multi-date networks outperforms the single-date networks. We also made a quick modification of the original network that we found on the paper. We just add some source, a digital elevation model, and we saw that we improve a bit the peak signal to noise ratio. So this is some screenshots. You can see on the left the input image, and on the right the reconstructed image. So you can see that the shadow area are quite well reconstructed, but in the completely cloudy areas we generate some blur in the image. The network is able to successfully remove this kind of shadows or this kind of hazy clouds. But when the cloud coverage is too thick, we can see that the reconstructed image suffers from blurry and strange artifacts. It's not really working well in the completely opaque areas. So the conclusion of our study is that using multimodal data, namely synthetic aperture radar and digital elevation model, improves the optical images reconstruction, and that is done quite easily with deep learning approaches because it's quite simple to perform some data fusion. And deep learning based methods have a reasonable computational cost because we can go large scale over thousands of images and in a reasonable processing time. And processing one entire Sentinel-2 image is like 10 or 20 minutes, so it's really quick. And we also found that the weekly supervised training could leverage the defect of the quality masks for pre-processing. Our code will be available soon on the CNES and INRAE GitLab and on GitHub. And we'll also present at the Force4G conference the decloud software. That is the base of all our work. So that was the first part describing one application for time series preprocessing, and now we'll enter the second part, applying super resolution on Sentinel-2 images. Here the goal was to check how super resolution can be useful for the remote sensing community, and we have developed an open source framework targeting super resolution for remote sensing users. So what is a super resolution? It works with generative adversarial networks. Generative adversarial networks are basically two networks that fight each other. There is a generator that tries to generate some credible images, and one discriminator which try its best to detect which images have been generated by G or which images are genuine. So the generator is trained against one GAN loss and one distance loss, which is composed of one L2 or L1 loss plus one perceptive loss, which is computed using the pre-trained VGG network. So you compute the features of the VGG network and you just measure the distance between these features. The discriminator is trained to found the real and the fake images. We used the remote sensing images provided by Dataterra, namely Sentinel-2 images delivered by Teia. We used the 10-meter spacing bands, namely red, green, blue, and near infrared. We are very lucky because spot spectral bands are quite the same, so it's more easy to do the processing of the spot 6 and 7 image, because we perform some radiometric correction to make them match the Sentinel-2 image using a linear model. We used approximately 250 scenes provided by Dynamis, and we resample the spot 6-7 images from 1.5 meters to 2.5 meters. This way we have a multiple of 4 to perform the super resolution against Sentinel-2 images, which are 10 meters spacing. And we trained our model using acquisition dates ranging from April to October 20. So this made a dataset of more than 150k patches of pairs of high resolution and low resolution images, and we sampled these patches regularly across all images across all the France mainland area. We used some state-of-the-art specifics borrowed from the following papers. We adapted them to remote sensing, because in remote sensing we don't work only on red, green and blue channels. So for instance, we apply the perceptive loss only on these channels, and we apply the L1 or L2 losses on every other channels. Our model is designed to avoid blocking artifacts in the output. This way we can generate a full high-resolution image in a fully convolutional way, tile after tile. We trained our model on the Janzé supercomputer from the IDRIS on one single GPU node. It took approximately 3 weeks. And for the inference, we can apply the model on one entire Sentinel-2 image using the OTB TF software. It took about 1 hour on Tesla V100 GPU. So now we'll see some beautiful images. The first series of images come from France, but the other came from other countries. So it's funny to see that the model eventually performed well on areas on which it hasn't been trained. So it's quite funny. This is the city of Tours in France. So this is the original Sentinel-2 image, and this is the output of the super resolution algorithm. So this is the Lisbon city in Portugal. So the model has not been trained on this area, but it can perform quite well. And we think that it has a good potential to be fine-tuned. So if we freeze a few layers of the model, we can train it more quickly with less data on anywhere in the world with new images. This is in China, in the Baodu city. This is also in China, and you can see that the houses or these constructions are quite strange. They do not look right. It's a bit strange, but the fields looks fine if you compare the original image and the super resoluted one. This new image is located in United States at Oklahoma City. So now you can download any Sentinel-2 image and apply our pre-trained network. You can get our code, it's open source, it's on GitHub, and it's easy to use with Docker. You can even use some NVIDIA GPUs supports, and you can generate a high resolution image in just 3 command line. So it's up to you if you want to play with it. You can also train the model, of course. So thank you for your attention, and you can ask me some questions by mail. Bye.
Okay, so thanks a lot, Rémi, for this presentation. I asked one question in the chat, but maybe some people have some questions. We have time for 1 or 2 because it's already quite late. So my question, Rémi, was: would these images, super resolved images, would they be used by photo experts? Because here there is no model-based reconstruction.
Hi, do you hear me?
Oui, et tu peux parler en français,
ok.
C'est peut-être plus facile.
Ouais, ça marche. Eh ben, c'est un peu la grande question. Il y a beaucoup de questions à se poser sur l'utilité de ces images. Et là, ce qu'on a fait dans un premier temps, c'est proposer un framework un peu générique pour que déjà on puisse entraîner des modèles et faire de la recherche avec ça. Maintenant, là, c'est vrai que je ne sais pas répondre à cette question aujourd'hui. Il y a beaucoup de choses intéressantes à tester. Alors, c'est sûr que pour de l'illustration visuelle, c'est très intéressant. Maintenant, est-ce que ça peut être utilisé pour peut-être mieux segmenter les images, en particulier pour ce qui est faire de la déconvolution pour, je ne sais pas, segmenter du parcellaire ou des routes ou des traits de côte? À mon avis, il y a des choses à étudier et sûrement des choses intéressantes à quantifier, mais c'est vrai qu'aujourd'hui, il n'y a pas beaucoup de gens qui ont fait des choses là-dessus.
D'accord. Ouais, ok. Ouais, c'est vrai, j'imagine que c'est douteux pour des photos experts, quoi.
C'est clair.
Alors, il y a une question dans le chat. Est-ce que tu peux utiliser un autre réseau que VGG pour le calcul de la loss function?
Oui, c'est assez simple de changer la perceptual loss. Même la loss VGG, en fait, c'est un peu flou comme concept. Il y a des gens qui utilisent certaines activations du réseau, d'autres personnes en utilisent d'autres, etc. Et en fait, je pense qu'on pourrait tout à fait utiliser un autre réseau et ça pourrait être intéressant de tester sur un réseau qui a été entraîné sur des images satellites. Et on peut aussi entraîner un réseau sans perceptual loss du tout, juste avec des loss L1, L2 et du GAN. Mais c'est vrai que le VGG va un peu créer des images
dans le domaine du visible qui paraissent un peu plus réels.
D'accord, merci. Une autre question?
J'ai une petite question pour Rémi. Tu as utilisé un réseau génératif pour la résolution. Typiquement, ces types de réseaux, comme il y a un espace latent, une taille fixe, donc il fixe la taille des images. Donc,
Oui.
comment tu te débrouilles pour changer la taille, pour t'entraîner avec une taille, après tu peux l'appliquer avec une autre en utilisant une structure convolutionnelle ou comment ça se passe?
Ouais. Alors en gros, je vais synthétiser ça. En fait, pour faire simple, on entraîne, pour l'entraînement, on fait comme tu dis, on utilise des images de taille fixe. Et ensuite, pour l'inférence, en fait, on va extraire une partie du tenseur de sortie, une région centrale du tenseur en sortie pour éviter de créer des artefacts dus aux effets de bord qu'il y a aux bordures du tenseur dans les convolutions. En faisant ça, en fait, on va diminuer les artefacts et bien sûr, plus on prend une marge élevée, moins on aura d'artefacts. Et bon, en théorie, ça, c'est une hérésie de faire ça parce qu'on aura toujours des effets d'aliasing, mais en pratique, on ne le voit plus dans les images. Voilà. Et ça nous permet d'appliquer sur des portions d'images très larges qui sont plus grandes que les images avec lesquelles on a entraîné le réseau.
Et le réseau n'a pas une structure purement convolutionnelle. Il y a
Si. Alors, le discriminateur, lui, il n'a pas une structure purement convolutionnelle.
Oui.
Mais par contre, le générateur, on l'a fait vraiment en full convolutionnel.
D'accord. Donc, tu pourrais éventuellement l'appliquer sur toute l'image sans faire du tagging.
Tout à fait. Si on avait assez de mémoire sur le GPU, on pourrait.
Oui. D'accord. Ok, super, merci.
Merci.